Have you ever, like, played a perfectly fair game of chance?
Oh, that is a really profound question to start with.
Right. I want you to really think about the mechanics of that for a second. Have you ever engaged in a wager, maybe a flip of a coin with a stranger, or a roll of the dice where you had absolutely no edge?
And the house had absolutely no edge either.
Exactly. A scenario where the past didn't matter at all, the future was entirely open, and the only thing governing the outcome was just the pure, unfiltered essence of randomness. It's a strange concept, isn't it?
It is strange, yeah. Mainly because human beings are practically hardwired to reject it entirely.
How do you mean?
Well, we are pattern matching machines. If you put a person in front of a roulette wheel,
Oh,
even if they logically know it's completely random, they will inevitably start looking for an edge.
oh, totally. Like looking at the board to see what numbers hit recently.
Exactly. We look for momentum, we look for hot streaks, we desperately look for some sort of hidden advantage. The idea of a truly fair game, a system where your best possible guess of tomorrow is just literally where you are today, is almost alien to our psychology.
Right, our brains just aren't built for a vacuum of information. And yet we're looking at a document today called M1L6.pdf.
Yes, the infamous M1L6.
At first glance, it looks like an incredibly dense mathematical paper, right?
Right.
It's just filled with calculus that looks like alien hieroglyphs.
It can definitely be intimidating.
But this text isn't just an academic exercise. It is actually the blueprint for how trillions of dollars change hands every single day.
That's the crazy part. It's the secret to how Wall Street prices your mortgage, your retirement fund, and basically global risks.
Yeah, this exact concept, the perfectly fair game, is the mathematical bedrock of the entire modern financial system.
It really is a rigorous and, frankly, a beautiful piece of mathematical literature. It takes us from the philosophical foundations of probability, like the way we literally define the universe of chance, all the way up to continuous time stochastic calculus.
And it does all this to create a framework for measuring risk, right?
Precisely.
Okay, let's unpack this. Our mission today is to decode this architecture. We're going to translate the intimidating calculus and the statistics into an intuitive, crystal clear mental model for you.
We aren't going to skip the hard math either.
No, absolutely not. But we are going to understand why it works. If you're tracking your own 401k, or if you've ever wondered why insurance premiums are priced the way they are, this is the hidden machinery operating behind the scenes.
It's the engine under the hood.
So let's step into the arena. The text opens with an observation about how modern quantitative finance papers begin. It says that for the last 2.5 decades, almost all literature in this field starts with the exact same incantation.
It's basically like a mathematical spell.
The phrase is, let omega FP be a probability space.
Let omega FP be a probability space. Whether it is explicitly written out in the very first paragraph or just hovering silently in the background of all the equations, that triplet is always there.
Always there.
Yeah, the author actually notes that its ubiquitous presence reflects the absolute dominance of probability theory over quantitative finance today. You just cannot model markets without first building this probabilistic universe.
Let me make sure I'm grasping the scale of this. We are literally defining the boundaries of reality for our mathematical model.
That's a great way to put it.
So let's build this universe for the listener right now. What is this triplet? Let's take them one by one, starting with omega.
So omega, which is represented by the uppercase Greek letter, is the sample space.
The sample space, okay.
Right. In probability theory, omega is the realm of all possible outcomes of an experiment. It is the absolute limit of what could happen.
Give me a simple example.
Sure. If you are flipping a single coin, your omega is just a set containing two items, heads and tails. That's it. Or if you are rolling a standard six-sided die, omega is just the set of numbers 1 through 6.
So it's like the multiverse of our game. It contains every reality.
Yes, but in finance, it scales up dramatically.
Like how dramatically?
Well, if you were looking at the stock market over the next year, omega isn't just a few numbers. Omega is every single possible future path that every single stock could ever take, down to the exact microsecond.
Oh, wow.
Yeah, it is a space of infinite, continuous possibilities. It is basically the raw material of the future.
Okay, so omega is the board we're playing on. It's every possible square we could ever land on.
Exactly.
I'm going to skip the middle letter F for just a second because the third letter, P, seems like it pairs really naturally with omega. What is P?
So P is the probability measure. If omega is the realm of all possible outcomes, P is the rule that assigns a likelihood, a mathematical weight, to the events inside that space.
Right, so omega tells you a coin can land on heads or tails.
And P is what tells you that a perfectly fair coin has a 50% chance of landing on heads. It translates the realm of raw possibilities into the realm of measurable likelihoods.
So P is the physical weighting of the dice we are throwing. It
Yeah.
dictates the gravity of our universe.
That's exactly it. And P must obey certain strict logical axioms, too.
Like what?
For example, the total probability of all possible outcomes in your omega space must add up to exactly 1 or 100%.
Oh, that makes sense.
Yeah, you cannot have a scenario where the chance of something happening combined with the chance of everything else happening equals 110%. The universe must be mathematically closed.
That makes intuitive sense.
Yeah.
We have the possibilities omega and we have the odds P, but that leaves the middle letter, the F.
Right, the filtration.
Yeah, and reading through this text, F seems to be the one that really brings time, and I guess the human experience of time, into the equation. F stands for the filtration.
What's really fascinating here is how the text defines this concept. The filtration is an indication of how information about a probabilistic experiment builds up over time as more results become available.
Builds up over time.
Yeah, the mathematical definition actually calls it an increasing family of events.
I was racking my brain trying to visualize this.
Yeah.
Because increasing family of events sounds a bit abstract.
It is abstract.
I came up with an analogy, and I want you to tell me if it actually holds up to the math.
Yeah.
Imagine we are playing a really high-stakes game of Texas Hold'em poker.
Okay, I'm with you.
The omega, our sample space, is every single possible combination of the 52 cards in the deck being dealt to the players and the board. It's massive, but it's finite.
I follow you. And the P?
The P, the probability measure, represents the raw, immutable odds of the game. It's the mathematical fact that drawing an inside straight is statistically far less likely than drawing a pair.
Right.
That's just the gravity of a 52-card deck.
That tracks perfectly. So where does the filtration come in?
The F, the filtration, is the actual chronological flow of the poker hand. Before the dealer shuffles, my filtration, my information set, is basically empty.
You know nothing yet.
Right. I know the rules, I know omega and P, but I know nothing about this specific reality. Then, the dealer pitches me my 2 hole cards. I look down, and I see 2 aces.
A great start.
Exactly.
Yeah.
And my filtration has just expanded. I have new, concrete information. The universe of possibilities, the omega, hasn't changed at all, but my knowledge of it has narrowed.
That is a very precise way to look at it.
And it continues.
Right.
The flop happens. 3 community cards are revealed, face up on the center of the table. My filtration expands again.
It grows.
Yeah, the turn card is flipped, then the river card. At each step of time, more cards are revealed. As time moves forward along the x-axis, my information set grows. I know more about the reality of the game, and the fog of unknown possibilities shrinks.
Yes. In mathematical notation, we would actually say your knowledge at time t is the filtration F sub t.
F sub t. Got it.
And here is why the text calls it an increasing family of events. You never forget the cards that have already been played.
Right, you can't unsee the flop.
Exactly. The information is strictly cumulative. Your knowledge at step 1, F sub 1, is fully contained within your knowledge at step 2, F sub 2, which is contained within F sub 3, and so on.
That makes total sense.
The filtration essentially models the undeniable one-way arrow of time and the relentless accumulation of human knowledge.
It's an elegant way to capture something so subjective. We take this messy human experience of, like, learning things as time passes and lock it into a rigorous, cold mathematical object. Just the letter F.
It really is beautiful.
And it occurs to me, in the real world, different people have different filtrations.
Yeah.
Like in the stock market, an insider trading illegally has a different F sub T than I do, sitting at home looking at Yahoo Finance.
Oh, you're hitting on a profound implication there. Much of modern market theory revolves around exactly that: who possesses what filtration at what time.
Information asymmetry.
Precisely. But returning to our core model, you need all 3 of these elements to do quantitative finance. You need the possibilities omega, you need the odds P, and you desperately need the structure of how information is revealed over time, F.
So once you have constructed that omega FP space, you have built the arena.
You've built the arena, and now you can introduce the most important inhabitant of that arena.
The martingale.
The martingale.
Which sounds like a bird, but it's not.
No, definitely not a bird. The source document notes that martingales are encountered through 3 distinct but closely connected ideas in probability, but we are focusing on them today as a specific class of stochastic process.
Now, fundamentally, what is it?
Fundamentally, a martingale is a stochastic process that has no drift. It is the mathematical embodiment of that fair, random game you brought up at the very beginning of our deep dive.
A process with absolutely no drift. Now, this is where our source material does something really interesting. It provides its first visual aid, and it's a completely unexpected image to find in the middle of a dense mathematical finance paper.
It really catches you off guard.
It's not a chart, it's not a graph. It's
Right.
a high-contrast, black and white photograph of a horse. Specifically, it's the profile of a horse's head, and the horse is wearing very specific equestrian tack.
Yes.
There are the normal reins coming from the bit in its mouth, but then there's a separate leather strap connected to those reins that runs down the horse's neck and attaches to the girth underneath the horse's belly.
It's a striking photograph, and it's a highly deliberate pedagogical choice by the author. In the world of equestrianism, that specific piece of tack, that leather strap connecting the reins to the girth, is literally called a martingale.
Okay, I have to admit, when I saw a picture of horse tack in a paper about stochastic calculus, I was a bit thrown. Why rely on a 19th century horseback riding metaphor for 21st century quantitative finance?
Because the physical function of the tack perfectly describes the mathematical function of the equation.
Okay, break that down for me.
We have to look at what that piece of leather actually does to the animal. When a horse is being ridden, especially if it gets agitated, energetic, or spooked, its natural instinct is often to toss its head violently upward.
Right.
If a horse throws its head too high, the rider loses leverage on the bit, and they basically lose control of the animal.
Yeah, you can't steer a horse if its nose is pointed at the sky.
Exactly.
Hmm.
The physical martingale, the strap, is designed with a very specific measured length. It allows the horse to move its head freely side to side and up and down within a normal, manageable range.
But then what happens?
But if a horse tries to throw its head aggressively upward, the strap catches. It pulls taut against the girth. It physically restrains the upward movement. It stops the horse's head from drifting too high.
It controls the upward drift. That's actually a brilliant physical metaphor. So, in horsemanship, a martingale stops the upward drift of the horse's head. And in mathematical finance,
In mathematical finance, a martingale is a process that has been mathematically stripped of its drift. It gets rid of the drift.
so it's flattening it out.
Right. Now, when we say drift in finance, we're usually referring to a predictable long-term directional trend.
Like the stock market going up over time.
Exactly. Historically, the broad stock market has an upward drift. Over decades, despite the crashes, the corrections, and the daily volatility, the overall market tends to go up and to the right.
Because economies grow.
Economies grow, populations increase, companies innovate, and, fiat currencies experience inflation. That underlying upward momentum is the drift.
But hold on, let me push back on this.
Yeah.
The entire point of finance, the whole reason people put their life savings into index funds or Wall Street banks build massive quantitative models, is to make money. We want that positive drift. We want the graph to go up.
Of course we do.
So why do quantitative analysts, literally the smartest mathematicians on the planet, spend their careers obsessing over processes that explicitly have no drift? Why study a fair game where mathematically nobody makes a predictable profit?
That is the crucial question. It seems entirely counterintuitive until you understand what they are actually trying to measure.
Which is risk.
Yes. Quants and probabilists love martingales precisely because they strip away the predictable, easy part of the equation.
The easy part being the upward trend.
Right. Think about it. If you have an asset with a massive upward drift, say a tech stock in a massive bull market, that sheer upward velocity can mask the underlying volatility. It hides the true nature of the noise and the risk.
Oh, I see.
By mathematically removing the drift, by transforming the asset's price path into a martingale, mathematicians can isolate and study the purely random statistical properties of the system.
That makes a lot of sense. So it's like putting a physical system in a vacuum chamber. You suck all the air resistance and gravity out of the room so you can see how a feather and a bowling ball actually fall in pure physics.
That is a perfect analogy.
We strip away the predictable momentum so we can put the pure, unfiltered randomness under a microscope.
You must isolate the noise to understand the risk. Furthermore, in derivative pricing, like figuring out the fair price of a complex options contract, you absolutely rely on a concept called the risk-neutral measure.
risk-neutral measure.
Yeah, we won't go too deep into the weeds of measure theory today, but in a risk-neutral pricing framework, discounted asset prices are mathematically forced to be martingales.
So it's non-negotiable.
Completely non-negotiable. Understanding the fair game is the absolute baseline for pricing anything. If you don't understand how a fair game behaves, you cannot accurately price the risk of an unfair real-world game.
Okay, we have to understand the vacuum before we can build the airplane.
Yeah.
To truly grasp how this driftless environment works, our source document dives into the concept of conditional expectations.
Yes, and this is where that filtration, that F we talked about with the poker game, comes roaring back into play.
The text defines the conditional expectation mathematically as E sub m, bracket y sub n, given f sub m for n greater than m.
Let's translate that mathematical notation into plain English.
Please do.
The E stands for expectation, or the expected value. You can think of it as the mathematically optimal guess of a value.
Right.
Y sub n is the actual value of some random variable, let's say a stock price at a future time m.
So y is the stock, n is the future.
Right. And that vertical bar, it's a crucial piece of syntax. It means conditional upon or given. Finally, f sub m is the filtration, the total information set available to us at the current time m.
Okay, so reading it left to right, E sub m bracket y sub n given f sub m translates to, what is my best mathematical guess of this asset's value at future time n, given absolutely all the information I currently hold in my hand at present time m?
Precisely, you got it.
The source emphasizes that what makes a conditional expectation completely different from a standard unconditional expectation is the information.
Unconditional expectation is asking a broad cosmic question, like, what is the average outcome of this game across all of time and space forever?
Whereas conditional expectation is grounded in reality.
Exactly. It asks, what is the expected outcome of this game right now, given that I've already seen the flop and the turn cards?
It's the difference between asking, what's the average temperature on Earth, versus what's the expected temperature in Chicago tomorrow, given that a cold front just moved through today.
The condition changes everything.
The text also introduces a related term here, an adapted process. It says a stochastic process, S sub t, is adapted to the filtration F sub t if the value of S sub t at time t is entirely known given the information set F sub t.
Yes.
That feels a bit circular to me. What does it actually mean, practically, for a process to be adapted?
Practically, it means the mathematical model isn't clairvoyant. It means the process doesn't get to peek into the future. A process is adapted if, at any given present moment t, your current information f sub t is perfectly sufficient to tell you exactly what the value of the process is right now.
So I don't need tomorrow's Wall Street Journal to tell me today's closing price for Apple stock.
Exactly. If your mathematical model requires tomorrow's newspaper to calculate today's value, the process is not adapted to today's filtration. It is violating the flow of time.
Ensuring a process is adapted is simply ensuring your math respects causality.
No time travel allowed.
Got it. And this brings us to the second visual aid provided in the document labeled Image 2. I want to spend some real time forensically detailing this graph because it perfectly visualizes the philosophical core of everything we've just discussed about martingales and expectations.
It's a very important graphic.
Instead of just describing the lines, let's ground this in a physical experience. Imagine you, the listener, are hiking up a rugged mountain trail.
A fitting setting for a random walk. Let's map the graph to this hike. On the bottom horizontal axis of our graph, we have time.
Right.
It starts at time 0 on the far left, moves to a point called S in the middle, and then moves further to a point called S on the far right.
Right. Time 0 is when you started hiking at the base of the mountain. Point S is where you are standing right now, pausing to catch your breath. And point S is where you will be an hour from now in the future.
Perfect.
Now, let's look at the actual path on the graph. From time 0 to time S, the past leading up to the present, we see a blue, jagged, highly volatile line moving up and down.
That blue jagged line is the physical trail you just hiked. It is historical fact. Underneath this section of the time axis, there is an arrow pointing from 0 to S, and it's labeled F sub S.
The filtration.
Yes, that arrow represents your filtration. Because you are currently sitting at time S, you have physically walked and observed this entire jagged path. It is fully locked into your information set.
I can look down the mountain and see every twist and turn I took. In the very end of that blue jagged line, sitting exactly on the vertical dashed line for the present time S, is a single blue dot labeled M sub S. That dot is my exact altitude on the mountain right now.
Yes, m sub s is the current known value of our adapted process. Now here is where the visualization of the martingale gets incredibly profound.
What happens to the right of that dot?
Yeah.
What does the math tell us about the path between the present moment, s, and the future hour, t?
This is the striking part of the image. From the dot m sub s extending out into the future toward time t, there is no jagged blue line. There is no predicted mountain trail going up or down. Instead, there is just a perfectly flat horizontal line cutting straight across the graph. It's drawn in red for the first half, then green for the second, but it is completely, perfectly flat.
It doesn't rise, it doesn't fall.
No, it stays locked exactly at the current altitude of m sub s, and it is labeled with the equation. Expectation of m sub t given f sub s equals m sub s.
That equation is the mathematical heartbeat of a martingale. Let's read it out loud in the context of your hike.
Yeah.
The expected value of your altitude at future time t, given the information of the trail you've hiked up to present time s, is exactly equal to your current altitude m sub s.
You've got it.
But wait, this is where my intuition breaks down. How can the future be a flat line? If I'm hiking a rugged mountain, I know my altitude an hour from now isn't going to be exactly where I am now. I'm going to go up over a ridge or down into a valley. Stock market doesn't just freeze in place for a week.
And the beauty of this graph is that it entirely acknowledges your point.
It does.
Yes. If you look at the far right of the image, exactly at future time t, there is a vertical bell-shaped curve drawn sideways along the axis. It's a normal distribution curve centered right on that flat line.
Ah, I see it. It's a bell curve showing probability.
If we connect this to the bigger picture, this graph is actually displaying two different dimensions of reality simultaneously. The bell curve at future time represents the actual uncertainty of the real world.
The possible outcomes.
Right. Your true altitude an hour from now could be way up high on a peak, or it could be way down low in a ravine. The bell curve shows the spectrum of all those potential outcomes. It acknowledges that there is variance, there is volatility, there will be a jagged path.
So the future is highly uncertain. The graph isn't denying that.
Exactly. It doesn't deny the uncertainty. But, and this is the foundational insight of a martingale, even though the future is entirely uncertain and you could land anywhere along that wide bell curve, your best mathematical guess of where you will land, given only the fair, driftless rules of the game you know today, is exactly where you're sitting right now.
Because it's fair.
Right. The flat line isn't saying the asset price won't move. It's saying that because the horse's martingale has stripped away the upward drift, the massive upward possibilities and the massive downward possibilities perfectly balance each other out in the equation.
The forces of up and the forces of down cancel each other out in my expectation. So my best guess today of tomorrow is just today. Because I have no edge, I have no predictable trend to rely on. It's the ultimate fair game.
That is the essence of it. And from this beautiful visual intuition, the source document transitions into rigid mathematical definitions, starting with discrete time martingales.
Right, let's look at how the math actually enforces this. Discrete time just means time moves in rigid, distinct chunks, right? Day 1, day 2, day 3, like turns in a board game rather than a continuous, smooth flow.
Exactly.
The text defines a discrete time stochastic process m sub t for t equals 0 to capital T as a martingale if it meets two specific conditions. The first condition is the expectation of the absolute value of m sub t is less than infinity.
The absolute expected value of the process must be strictly less than infinity. This is known in mathematics as a standard integrability condition.
Okay, in plain English.
In plain English, it simply means the process, the game you are playing, cannot explode to infinity. The game has to have bounded, measurable rules.
You can't play a casino game where the payout might literally be infinity dollars. The universe would break.
Exactly. It ensures the mathematical machinery doesn't divide by zero or encounter paradoxes.
Makes sense.
The second condition is the algebraic version of the equation we just saw on the graph. Expectation of m sub t plus 1 given f sub t equals m sub t.
The conditional expectation of the process at tomorrow's time step t plus 1, given today's filtration f sub t, is just today's value, m sub t.
That's our flat line on the mountain.
But then the source does a fascinating little algebraic trick here. It asks, what happens if we take the unconditional expectation of both sides of that equation?
Yes. If you apply a broad, unconditional expectation to a specific conditional expectation, you get a very elegant result. The equation simplifies to the expectation of m sub t plus 1 equals the expectation of m sub t.
The expected value of tomorrow is equal to the expected value of today.
Right. The author notes that this simplification relies on a fundamental theorem in probability called the Tower property of conditional expectations.
Okay, tower property of conditional expectations. That sounds like something out of a wizard spellbook. I need a concrete translation for this one.
Think of it as a strict hierarchy of guessing. The Tower property mathematically proves that your best guess today of what your best guess will be tomorrow is simply your best guess today.
Hold on, let me make sure I'm getting this. My best guess today of what I will guess tomorrow is just my guess today. Let me try an analogy.
Go for it.
Suppose I'm trying to guess the high temperature for next Friday, and it's currently Monday. My best guess today, looking at historical averages, might be 70 degrees. Now, I know for a fact that tomorrow, on Tuesday, I will check the weather radar, my filtration will expand, and my guess will likely change. Maybe I see a storm coming, and I revise my guess to 65, or maybe it's sunny and I revise it to 75.
Correct. Your future filtration will alter your future expectation.
But, and I think this is what the Tower property is getting at, sitting here right now on Monday, without access to Tuesday's radar,
Yeah.
I have no idea if that new information will be bullish or bearish for the temperature.
You don't know the future news.
Right. I can't bias my guess upward or downward based on information I don't have yet. So my best guess of what my Tuesday guess will be is still just 70 degrees. I can't anticipate the direction of my own future knowledge.
That is a flawless explanation. You cannot pre-compute the arrival of new information. If you could somehow know today that tomorrow's news will make you revise your estimate upward, then it wouldn't be tomorrow's news. You would have already incorporated it into today's estimate.
That makes perfect sense.
The Tower property mathematically guarantees that your expectations remain perfectly consistent across different time horizons, as long as there is no new information to update them. It prevents paradoxes in your forecasting.
It's so deeply logical when you frame it around the limits of human knowledge. Now, the source document takes these discrete, chunky steps of time and generalizes them into continuous time.
Yes, moving from the board game to the real world.
Instead of t equals 0, 1, 2, we define time as t in r+, meaning time flows smoothly, infinitely divisible, without interruption. The core martingale condition remains philosophically the same. Expectation of m sub t given f sub s equals m sub s for any point in time that is less than or equal to t.
And it is at this exact moment in the text that the author introduces the classic quintessential example of a continuous time martingale.
A big one.
The foundational process of modern finance, Brownian motion.
Brownian motion. This is a term that bleeds over from physics all the time. If I recall correctly, it was originally observed by a botanist named Robert Brown in the 1800s.
That's right.
He was looking through a microscope at tiny grains of pollen suspended in water, and he noticed they were constantly jittering around, moving in completely erratic, unpredictable paths, even though the water was perfectly still.
Yes. Brown observed it, but he couldn't fully explain it mathematically. It actually took Albert Einstein in 1905 to provide the physical explanation. The pollen grain is constantly being bombarded by invisible water molecules from all sides.
And because it's random.
Because the molecules are hitting it randomly, the pollen is pushed in a perfectly erratic, continuous path. Decades later, a mathematician named Norbert Wiener rigorously defined this chaotic movement as a pure stochastic process.
And how does that relate to finance?
In finance, we use Brownian motion to model the continuous, unpredictable bombardment of news and trading activity on an asset's price.
And this brings us to one of the most fascinating parts of our deep dive, the Levy revolution in Brownian motion. Our source material contracts two entirely different ways to mathematically define a Brownian motion. It places the classical definition side by side with something called Levy's martingale characterization.
And the differences between them are subtle on paper, but incredibly profound for how we understand risk. Let's walk through the two sets of rules side by side.
Let's do it.
Let's start with the classical rules. To prove a stochastic process, W sub t, is a Brownian motion under the classical definition, it must satisfy four strict conditions. First, W sub 0 equals 0 almost surely. The process must start at 0.
Rule 1. Start at the origin. That's simple enough. Both the classical and Levy sets of rules agree on this one.
Second, the sample paths of the process must be continuous almost surely.
Rule 2. No teleporting. If I'm drawing the path of the pollen grain on a graph, I can't lift my pen off the paper. The line might be infinitely jagged, but it cannot have sudden gaps or jumps. Again, both classical and Levy agree on this.
This is where the two philosophies diverge. The third classical rule demands that the process has independent increments.
Independent increments. What does that mean exactly?
This means that the change in the process between time 1 and time 2 is completely statistically independent of the change between time 3 and time 4.
So the pollen grain has absolutely no memory. The fact that it was just pushed aggressively to the left a millisecond ago dictates absolutely nothing about whether it will be pushed left or right in the next millisecond. The past has no bearing on the future momentum.
Exactly. And the fourth classical rule is the most restrictive. It states that these independent increments must be normally distributed.
A bell curve.
Yes. If you look at the change in the process over any time interval t minus s, that mathematical change must be drawn from a perfect Gaussian normal distribution, a flawless bell curve, with a mean of 0 and a variance exactly equal to the length of the time step, t minus s.
Okay, let me summarize the classical rulebook. Start at 0, be continuous, have 0 memory, which is the independent increments, and every single movement must fit neatly inside a perfect, predictable bell curve.
That's the classical view.
That sounds very neat and tidy. But now, let's look at Paul Levy's rules. Levy keeps the first two, start at 0, and be continuous. But he takes rules 3 and 4, the 0 memory and the perfect bell curve, and he basically throws them in the trash.
He discards them entirely. Instead, Levy introduces 2 new rules based strictly on martingales.
Okay.
Levy's Rule 3 simply says the process W sub t itself must be a martingale with respect to its filtration F sub s.
So it must be a fair game with no drift.
And Levy's Rule 4 says that the squared process minus time, specifically the equation absolute value of W sub t squared minus t, must also be a martingale with respect to F sub s.
Okay, this raises an important question. Why did Levy do this? To a layperson, statistical independence and the normal distribution bell curve seem like the defining fundamental features of randomness. Why replace those highly descriptive statistical properties with these 2 abstract martingale conditions?
To understand Levy's genius, you have to look at the reality of applying mathematics to messy, real-world systems like financial markets.
They aren't perfect.
No, they aren't. Trying to empirically prove that every single movement of a stock price is perfectly independent of the last movement and conforms perfectly to a Gaussian normal distribution all the way out to the furthest, most extreme tails of the bell curve is practically impossible.
Right. I mean, anyone who lived through the 2008 financial crisis knows that stock market returns are famously not perfectly normally distributed. We talk about fat tails.
Exactly, fat tails.
A perfect bell curve predicts that a massive market crash should only happen once every 10,000 years, but in reality, they happen every decade or two. The classical assumption is really fragile.
You're hitting on the core problem Levy was trying to solve. The classical rules require you to make massive, fragile assumptions about the microscopic statistical nature of the noise. Levy found a better way.
By using martingales.
Yes. Proving that a continuous process has no predictable drift, proving it is a martingale, is mathematically far more robust. And his fourth rule, proving that the squared variation is also a martingale linked to time, essentially just proves that the variance scales linearly as time moves forward.
Okay.
Levy mathematically proved that if you have a continuous process with no drift and its variance scales smoothly with time, the mathematics force it to be a Brownian motion. The independence and the bell curve normality emerge naturally from those 2 foundational martingale conditions. You don't have to force them in as fragile assumptions from the start.
It's an incredible shift in perspective. It's like, instead of trying to inspect every single microscopic brick in a skyscraper to make sure it's flawlessly manufactured, you just conduct a stress test on the structural integrity of the steel foundation.
I like that.
If the foundation holds, if the martingale conditions are met, that proves the building is solid, and you don't need to worry about the individual bricks.
A very apt way to describe it. Levy gave mathematicians a much deeper, more verifiable way to characterize pure randomness.
Okay, let's take a breath, because here's where it gets really interesting. We've established the arena, we know what a martingale is, we understand Brownian motion. But if I'm a quant on Wall Street building an algorithm, how do I physically construct a fair game out of raw, continuous market data?
That requires a new kind of math.
And that brings us to Ito integrals and the martingale representation theorem. The source text reveals a profound, inseparable, two-way relationship between Ito calculus and martingales.
It is arguably the most important relationship in continuous time finance. The text states unequivocally, let g of t, w sub t be a function satisfying certain standard technical conditions. If you take the Ito integral of that function with respect to Brownian motion, the integral from 0 to t of g of t, w sub t d, w sub t, that integral is always a martingale. Always. Every properly constructed Ito integral is inherently a driftless, fair game.
But the text goes even further. It asks, does the converse hold true? We know Ito integrals are martingales, but can we represent any martingale as an Ito integral?
And the answer is a resounding yes.
Hmm.
This is known as the martingale representation theorem.
It's a monumental theorem. Think about what it's implying. It essentially says that any risk, any fair game, any complex martingale floating out there in a Brownian universe can be perfectly mathematically replicated by continuously trading in the underlying Brownian motion.
That's right.
Wait, is this the mathematical justification for dynamic hedging?
Exactly. It is the absolute core of Wall Street options desks. When a bank sells you a complex customized derivative, they take on massive risk.
Because they have to pay out if it hits.
Right. But the martingale representation theorem guarantees that because that derivative's payout can be represented as an Ito integral of the underlying asset's risk, the bank can theoretically hedge that risk perfectly by continuously buying and selling tiny amounts of the underlying asset as time moves forward. The math proves that a perfect replicating shield can be built.
That is wild. The math proves that risk can be perfectly offset. To prove just how powerful this mathematical machinery is, the source text walks us through a specific, rigorous proof.
Yes, the proof for the squared Brownian motion.
It wants to prove a very specific statement, that the expected value of a squared Brownian motion at time t, written as e bracket w squared of t, is simply equal to t. And it wants to prove this using only Ito's lemma and this new golden rule that Ito integrals are martingales. I want you to walk me through this derivation, but let's translate the algebra into audio-friendly concepts. No reading raw latex code.
I will happily guide us through it conceptually. We start by looking at our target. We want to know the expected value of our Brownian motion squared at the final bell, time t. So we start with our ending value squared.
Okay, I have my final altitude on the mountain, and I've squared it.
Now, we apply Ito's lemma, which is the fundamental chain rule of stochastic calculus. It tells us how to break apart functions of random processes. When we apply Ito's lemma to our squared value, it shatters the equation into three distinct pieces.
What are the three pieces?
The first piece is just our starting value squared. The second piece is a standard deterministic integral relating to time. Because we took up the second derivative of our squared function, this piece simplifies beautifully down to just the regular integral of time, dtt.
Okay, so we have the starting point plus a smooth flow of time.
And the third piece is the stochastic part. It is an Ito integral that captures all the chaotic, jagged noise of the Brownian motion along the way.
Let me visualize the shattered equation. Our final squared value is equal to our starting value squared plus a smooth time component plus a chaotic Ito integral noise component.
Correct. Now we simplify. We know from Paul Levy and the classical rules that a standard Brownian motion always starts exactly at 0. So that first piece, the starting value squared, is simply 0 squared. It vanishes, we drop it.
Love it when math deletes itself. We are left with just the smooth time component and the chaotic noise component.
Precisely. Now, we take the expectation of both sides of this equation. We want to find the expected average outcome. The expectation of our final squared value equals the expectation of the smooth time piece plus the expectation of the chaotic noise piece.
And this is where we use the golden rule we just learned.
Yeah.
That chaotic noise piece is an Ito integral. And the text just told us that all Ito integrals are martingales. And we know that martingales are fair games with absolutely no drift. Therefore, the expected value of that massive, nasty-looking chaotic noise integral is simply 0. The upward noise and downward noise perfectly cancel each other out in expectation.
Exactly. The stochastic noise term entirely vanishes under expectation. It just drops away. So what are we left with? We are left with only the expectation of the smooth time integral.
And the integral of time from 0 to t is just t. And the expected value of a constant t is just t. Therefore, the expected value of the squared Brownian motion at time t is simply equal to t. That is beautiful. We just bypassed pages of complex stochastic calculus simply by realizing the expected value of the noise was 0.
It is a very elegant, powerful proof of how useful the martingale property is. The source also includes a brief technical aside here about something called Fubini's theorem.
Oh, right, Fubini.
During our derivation, we casually swapped the order of operations. We had an expectation of an integral, and we conceptually treated it like the integral of an expectation.
Is that illegal in math?
Without Fubini's theorem, yes, it can be. Fubini's theorem is the rigorous analytical rule that gives mathematicians the legal permission to exchange the order of integration and expectation.
Why does the order matter so much?
Think of it like calculating the total volume of a loaf of bread. You can slice the loaf vertically, measure the area of each slice, and add them all up. Or you could slice the loaf horizontally, measure those layers, and add them up. Fubini's theorem proves that as long as the bread meets certain reasonable conditions, both methods will give you the exact same total volume. It's a technical detail, but it's the engine that makes these stochastic calculations viable.
It's good to know we aren't breaking the fundamental laws of calculus by slicing the bread sideways. All right, so we've established that Ito integrals are the heartbeat of martingales. As we move deeper into the text, the source gives us a few more properties of Ito integrals.
Like linearity.
Right, meaning you can break complex integrals apart and something called Ito isometry, which is a powerful way to calculate the total variance, the total wobble of a path over time. But then the author asks a very practical, almost exam-style question.
Yes, the author asks, suppose you are given a brand new continuous stochastic process, let's call it y of t, which solves a standard stochastic differential equation, an SDE. How do you quickly know if this new process is actually a martingale?
The text gives us what I'm going to call the ultimate drift test.
The drift test is remarkably straightforward once you understand Ito integration. Any standard SDE can be broken down into two distinct parts. When you integrate it, you get a dt term, which represents the smooth deterministic drift of the asset, and you get a dw of t term, which is the Ito integral representing the random chaotic noise.
And as we just proved with our squared value derivation, we know the Ito integral noise part always has an expectation of exactly 0.
Correct. Therefore, if you take the expectation of the entire process y of t, the noise vanishes, and the only thing left standing is the dt term. Now, for the overall process y of t to be a perfectly fair game, for it to be a martingale, its expected value cannot change over time. It must be that flat line on the mountain graph.
Okay.
Therefore, the drift term, the dt portion of the equation, must be exactly equal to 0.
So y of t is a martingale if and only if the drift term is exactly 0. If there is even a sliver of a dt term left over, it has a drift and it fails the test. To prove we actually understand this, the source document provides an interactive exercise. It gives us 3 different stochastic processes, and we have to determine if they are martingales. I'm going to test my intuition on these, and I want you to confirm the reality with the hard math.
I am ready with the chalk. Let's look at the first example.
Example 1, y of t equals w of t plus 4t. Okay, let me think through this. W of t is a standard Brownian motion. We know from Levy that this is a martingale. It's pure noise with no drift. But then we are actively adding plus 4t to it. That means as time t ticks forward, the value of this process automatically goes up by a factor of 4. That is a massive, predictable upward escalator. My intuition says this unequivocally fails the test. It is not a martingale.
Your intuition is spot on. Mathematically, if we calculate the differential equation for y of t, we get dy of t equals 4 dt plus dw of t. Applying our drift test, we look strictly at the dp term. The dt term has a coefficient of 4. Because 4 is not 0, the process has a deterministic upward drift. It fails. It is simply a Brownian motion with a strong upward drift, not a martingale.
Okay, 1 for 1. Let's look at example 2. Y of t equals w squared of t plus k, where k is just some given constant number like 5 or 100. Does the answer depend on what k is?
Good question.
My intuition goes back to Paul Levy again. Levy taught us that w squared of t minus t is a martingale. We had to subtract time chi to cancel out the inherent compounding drift of squaring a Brownian motion.
That's right, the -2 part.
In this example, we aren't subtracting t. We're just adding a flat constant k. Adding a flat constant doesn't stop the compounding drift. It just shifts the starting line of the race up or down. My intuition says this also fails, regardless of what the constant k is.
Again, correct. Let's prove it rigorously using Ito's lemma. We apply Ito to the function f of w equals w squared plus k. When we run the calculus, the SDE for the process becomes dy of t equals dt plus 2w of t dw of nu.
Okay.
We isolate the drift term, which is the dt2. Its coefficient is 1. Since 1 is not 0, the dynamics of y of k possess a positive drift. It's not a martingale, and as you guessed, since the constant k disappears entirely during differentiation, the result is completely independent of the value of k.
2 for 2. Now for the final example, and this one looks tricky. Example 3. Y of t equals W1 of t times W2 of t. We're taking two distinct standard Brownian motions and multiplying them together, but the source adds a specific twist. It says these two Brownian motions have a correlation of rho.
Yes.
My intuition. Honestly, I'm a bit stuck here. We are multiplying two random fair games together. Does correlation magically create a drift? If they move together, maybe they compound each other.
This is a complex scenario, and it requires something called the Ito product rule. When you calculate the differential of the product of two correlated Brownian motions, the SDE expands into three terms. W1 of TDW2 of t plus W2 of TDW1 of t plus a third term, OODT.
Ah, there it is. The Ito product rule spawned a DDT term out of nowhere.
Exactly. The cross variation of two correlated Brownian motions naturally generates a deterministic drift equal to their correlation coefficient, rho.
But why? Why does multiplying two correlated things create a drift in the real world?
Think about it this way. If two stocks are highly positively correlated, let's say two oil companies, when one jumps up due to a news event, the other is very likely jumping up at the exact same time. When you multiply their values together in a mathematical model, you are squaring those simultaneous positive jumps. You are multiplying positive by positive, creating a massive artificial upward momentum. If they both drop simultaneously, you are multiplying negative by negative, which also creates a positive upward momentum in the product. This compounding effect creates a relentless upward drift that wouldn't exist if they are moving completely independent of one another.
That makes so much sense. The correlation ensures they reinforce each other's direction, creating a drift. So, applying the drift test to the math, we look at that DT term. It is OODT. For this product y of t to be a martingale, that drift must be exactly zero, which means the correlation, rho, must equal zero.
Yes. The product y of t is only a martingale if rho equals zero. In statistical terms, this means the two Brownian motions must be completely 100% independent of each other. If they have even the slightest correlation, positive or negative, the process develops a drift and ceases to be a fair game.
That is a profound insight for anyone building a portfolio. You think you are diversifying by holding two different assets, but if they are correlated, you are mathematically generating a compounded drift profile you might not even be aware of.
It absolutely is. And this mastery of the drift test leads us perfectly to the grand finale of our source document, the culminating lesson. This is arguably the most important mathematical structure we've discussed today. Exponential martingales.
Everything we've done so far, all the analogies, all the proofs, has been building up to this specific formula. The text asks, how do we take an exponential process and turn it into a perfectly fair martingale? Before we do the math, why is exponential growth so crucial that it gets its own dedicated finale?
Because in the real world of finance, asset prices generally grow exponentially, not linearly. A stock doesn't grow by a fixed $5 every single year. It grows by a percentage, say 5%. Compounding interest is an exponential function. Therefore, if we want to model realistic asset prices, we need a way to model random processes that exist in an exponential domain. But to price derivatives on those assets, we need to know how to make them fair in our risk-neutral measure. We need to know how to strip away their exponential drift to create an exponential martingale.
Okay, let's set up the problem exactly as the text does. We start with a generic underlying stochastic process called y of t. Its equation is dy of t equals f of t dt plus g of t dw of t. So it has some generic unknown drift f of t and some generic unknown volatility g of t.
Correct. Now, we define a completely new process, let's call it z of t, which is simply the exponential of our original process y of t. So z of t equals e to the power of y of t.
And the ultimate question the author poses is this: how must we carefully, surgically choose that underlying drift function, f of t, so that our new exponential process z of t is a perfect driftless martingale?
To solve this, we must rely on our trusted tool, Ito's lemma. We apply Ito to our new exponential function, z of t equals e to the power of y of t. Now, the derivative of an exponential function is just the exponential itself, which makes the calculus slightly recursive, but very elegant. After applying the first and second derivatives required by Ito's formula, the equation expands significantly.
The text gives us the expanded result. Z equals e to the y of t times, in parentheses, f of t plus 1/2 g squared of t dt plus e to the y of t times g of t w of t.
Yes. And because the term e to the y of t is just our original definition of z, we can substitute z of t back into the equation to factor it out and make it cleaner. We get dz equals z of t times, in large brackets, f of t plus 1/2 g squared of t dt plus g of t w of t.
Okay, I am staring at this equation. I see the large brackets. Inside, I see a dt term, and I see a dw of t term. And I remember the drift test we just mastered. For z of t to be a driftless martingale, the entire coefficient attached to the dt term must equal absolutely 0.
Proceed. What is the entire coefficient of the dt term?
The coefficient is f of t plus 1/2 g squared of t. So to make this an exponential martingale, we must mathematically force f of t plus 1/2 g squared of t to equal 0.
Which means
We can solve for f of t using basic algebra. We move the half g squared to the other side. F of t must equal negative 1/2 g squared of t. F of t equals negative 1/2 g squared of t.
if we connect this to the bigger picture, this specific algebraic adjustment is a monumental discovery in finance. Look closely at what that equation is saying. F of t is the drift. G of t is the volatility, the variance. The math dictates that to make an exponentially growing asset into a perfectly fair game, you must actively subtract exactly half of its variance from its growth rate.
Whoa.
This reveals the fundamental, inescapable interaction between exponential growth and volatility. Volatility literally drags down exponential compounding.
Volatility drag. I've heard that term before.
Think about it in real-world terms. If you have a $100 investment and it experiences intense volatility, say it drops 50% one year down to $50, to get back to your original $100, you don't just need a 50% gain next year, you need a 100% gain.
Oh, because you're starting from 50.
Exactly. The more volatile an asset is, the more its geometric return is punished and dragged down compared to its simple arithmetic average. That negative 1/2 g squared of t term is the exact mathematical penalty for risk. It is the cost of volatility.
That is incredible. Volatility isn't just background noise. It mathematically eats away at your exponential drift. If you have a highly volatile 401k, that noise is literally acting as a gravity well, pulling down your compounding interest. So returning to our original y of t process, we plug that specific penalized drift back into the exponent. The text provides the final simplified form for the exponential martingale. We're going to translate it into a concept rather than reading the raw
Easy
symbol.
do.
To find the fair value of an exponentially growing asset over time, you take your starting value and you multiply it by an exponent. Inside that exponent is a tug of war. You have the unpredictable, chaotic noise pushing you around, but you also have exactly half of your variance constantly pulling you back down, acting as a permanent penalty for the volatility of the ride.
That is a brilliant translation. That tug of war is the exponential martingale. And the source document concludes by noting that we have actually just derived a much more general and staggeringly important result. This specific exponential martingale formula is the exact mathematical foundation of the Black-Scholes model for pricing options. It is how the entire global financial industry models asset prices in a risk-neutral world.
It is stunning to realize that all of this complex theory builds up to something so incredibly applied. We've taken a massive journey today. We started at the absolute ground floor, defining the boundaries of reality with the omega FP probability space. We imagined the multiverse of outcomes, the physical weighting of the dice, and the gradual flipping of poker cards to represent the expansion of our filtration in human knowledge.
We then visualized martingales using the physical tack of a horse, realizing that to study risk, we must restrict upward drift and isolate pure randomness. We hiked the jagged mountain trail of conditional expectation, recognizing that in a perfectly fair game, our best guess of tomorrow's altitude is just today's altitude.
We contrasted classical Brownian motion with Paul Levy's elegant martingale characterization, learning that testing the structural integrity of the foundation is better than checking every individual microscopic brick for a perfect bell curve. We used Ito calculus to prove the martingale representation theorem, realizing that dynamic hedging is mathematically possible. And finally, we derived the exponential martingale, uncovering the hidden penalty that volatility imposes on compounding growth.
So what does this all mean? We've just spent this entire deep dive meticulously proving how mathematicians get rid of the drift to isolate a perfectly fair, predictable, driftless game of expectation. And as we just discussed, these exact equations, specifically the exponential martingale, are the fundamental building blocks used by quantitative analysts to model the massive, real-world financial markets we all participate in.
They are the hidden architecture of the global economy. But I want to leave you, the listener, with a final thought today, something to ponder long after this deep dive ends. Financial markets are famous for not being fair. They are driven by intense human emotion. They are driven by corporate greed, by irrational panic, by FOMO, by massive, unpredictable upward and downward drifts that defy logic. If the absolute core mathematics of quantitative finance relies entirely on the foundational assumption of a perfectly fair, driftless game in a vacuum, what does that say about the invisible gap between this beautiful, elegant mathematical theory and the messy, volatile, deeply human reality of the markets we actually invest our life savings in? Is the math truly describing human reality, or is it just a perfectly balanced horse martingale trying desperately to restrain an animal that just wants to run wild?
It is the great paradox at the heart of quantitative finance.
Thank you so much for joining us on this deep dive into the hidden architecture of risk. We invite you to step out and explore your own Omega FP probability spaces. And until next time, keep questioning the drift.